in the second week of May, without any doubt whatsoever. And in fact, we're probably going to, we might be in lab on Monday by the end of the day. I want to finish some basic electricity, because the first thing we're going to do when we go out in lab is we're going to do some electricity. What you're going to find is that as a mechanic who fixes most things, having a basic knowledge of electricity doesn't just come in handy a lot of times. A lot of times you can't fix it unless you understand some very basic electricity. So the first thing we're going to do in lecture, real mechanic stuff, is we're going to talk about electricity. And then the first thing we do in lab is we have some mock-ups that pretend airplane, and we're going to apply power to it, and we're going to use a meter and measure volts and ohms and amps and try to get good with that meter. Yeah. 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 That's what, good. Well, thank you very much. I'll give you that $20 for saying that after class is over. But I'm totally serious in that I was really lucky. My grandfather was a high school physics teacher, and so when he was seven, he retired. When he was seven, he retired. He was the principal of Orosi High School the day he retired. He taught physics at Orosi High before he became the principal. In any case, he didn't believe. This is back in the day when you could work on a car without having to have a computer to hook up to it. So I got to hang out with my grandfather in his garage, and we fixed stuff. He had a magneto, and we did spark plugs and did electrical work and overhauled engines and a bunch of stuff. So I was really, really lucky that I got a chance. Somebody was showing me how to use tools and how to do stuff. And I think people work on cars less now than they used to, because you need a big $10,000 computer to hook up to do a bunch of stuff of it. And our society is different than it was. In any case, I think I'm ranting here a little bit, so you'll have to forgive me. The youth of today, that would be you. The people who are in their late teens and early 20s right now, generally, on average, have not used tools or fixed things as much as the average person in their late teens or their early 20s did 20 or 30 years ago. It's different. I'm not arguing about why it's that way, and you can argue about why it's good and bad. I personally, I'm prejudiced. I am prejudiced, or maybe a better word is I am biased. I think that every single person ought to have some mechanical skill. So if the light doesn't work, can you figure out if it's the light bulb, or do you need to go outside and use and flip the circuit breaker? Where is the circuit breaker? What do they look like? How do you flip a circuit breaker? These are things that everybody needs to know. Whether you own a home or you rent an apartment, everybody needs to know that sort of thing. What if you put in a new light bulb and it doesn't work? Am I going to call a technician and pay them $125 to come out and just look at the house? Really, I probably ought to go find a circuit breaker and flip it back and forth a couple of times and see if that does the trick. So, I guess I'm done ranting. So, therefore, since, how many things do you own that don't use electricity? It's like, if you even have a freaking bicycle. Well, my bicycle uses electricity because I have a headlight on the front and a tail light in the back, and I've got this little gauge that hooks up to the bicycle, tells me how fast I'm going. In any case, if you can understand basic electricity. Now, I got to tell you, though, that a lot of people look at electricity and it scares them, or it looks very confusing, or it seems really, really hard. And that is normal, that is typical for people to look at electricity and go, inside they're going, ah! Okay, so if right now, inside of you, somebody says electricity and you're going, ah! Because you had it in a science class and you didn't understand anything the instructor was talking about, and now you're presented with it again and you don't want it. I hear you. I understand. I got very lucky as a teacher, and when I got out of the U.S. military and I got my first job teaching, it was at a mechanic school, and I taught electricity. And I taught 2 hours of electricity in class, and then I had a 6-hour lab. And then the next day, I had the exact same students for 2 hours of electricity lecture and 6 hours of lab. So whatever I screwed up the previous day and I didn't teach it right, the next day I got to do it over again. I got to do it better. So I'm not saying I am the best teacher of electricity on the planet. You're just going to have to believe that that's true even if I don't say it. I'm just kidding. So we're going to do electricity. To get a basic understanding, you need to understand a little bit about physics. People in here have taken physics in high school. How many people? 2 people out of 9. All right. How many people are going to take physics in high school? No. Okay. So 2 out of 9. All right. You're going to take. That's over. Grandfather, he might have something to say to you. Okay. So when I say physics, you don't have to freak out. We're not doing very much math. The only math we're going to do is we're going to have to be able to add, subtract, multiply, and divide, and you can use a calculator if you want to. I'm going to say that again. The only math we're going to do is add, subtract, multiply, and divide, and you can use a calculator. But the math we're going to do is going to be so easy you probably aren't even going to want a calculator, even on the 17 math questions that are on the test. No, there are no quadratic formulas. Somebody's happy that we aren't having quadratic formulas? We're gonna fly quadcopters, but we're not going to apply mathematical formulas to do it. All right, so I want to talk about electrons because they're awesome. Electrons travel approximately at the speed of light. You don't have to memorize the speed of light, but it's 300 million meters per second or 186,000 miles per second. You don't have to write those numbers down. Just to get you a perspective, electrons travel at the speed of light, and light's that fast. The moon is about 250,000 miles away. So to go to the moon and to come back is about 500,000 statute miles. Well, 186,000 statute miles per second takes about a second and a half to go to the moon and about a second and a half to come back. So if you had a mirror on the moon and a really, really good laser, you could turn on the laser and 3 seconds later it would hit you, bouncing off of the mirror on the moon coming back. That's the speed of light. And the speed of electrons in wires is almost that fast. For practical purposes, as far as aircraft mechanics, it's pretty close to instantaneous. Because we can't measure, if it's only 27 feet, how long does it take? 0.00000000001 seconds. You can't estimate how long that is. So it's ridiculously fast. All right. Electrons are negatively charged. Back in the old days, you don't have to write this part, but back in the old days, they thought electrons were positively charged, and they were wrong. You don't have to write it down, but that was called the conventional theory of electricity. We're going to use the real theory of electricity, where electrons are negatively charged. So if electrons are negatively charged, and you know anything about static, well, let's say only 2 out of 9 of you have taken physics, all right? So if you have, anybody ever heard of static electricity? That's where you take your younger sibling with the big hair and rub their head on the rug and then see if their hair will be attracted to the wall. Has anybody ever done that? Okay, it doesn't work. It doesn't hold up people very well. All right. Well, static electricity means that something has more electrons than and another thing has too few electrons. This is where the phrase opposites attract works. So a negative electron is attracted to a place where it's positive. A positive item means there's not enough electrons. Something has taken electrons away from it. The electrons are just trying to get back to a place that is ready to accept the electrons. Effectively, that's a battery. Batteries are just a chemical and mechanical device that you pull electrons off of one side of the battery and shove them on the other side, and they're negative, and where you come from is positive, so they're all going to try to go back to the other side. So if you hook up a battery, say to a light bulb, and the light bulb comes on, the electrons are going through the light bulb, but the electrons are going through the light bulb and the wire, and they're going to the positive side of the battery, and after a while, it evens out. You don't have any more extra electrons, and the other side of the battery is now full of electrons. So now electrons try to move, so that means the battery is dead. So electrons are negatively charged. And I already said that part there. And really you have to be missing electrons. You can't just say, well, you didn't add any electrons, so it's positive. No, you have to pull some electrons off of it, and now it becomes positively charged. And that's really, like I said, that's what the positive side of a battery is. Electrons got pulled off of the positive side, so there's a hole trying to suck in the electrons. And if you give them a path to travel, say a wire, then it'll pull the electrons in from the other side. And those negative electrons, they're chomping at the bit. They're trying to get back to where there's not enough electrons. As soon as you hook up a wire, they will move. So if you have electrons going through a wire or a conductor is that person that's on a train that walks around asking for your ticket. In electronic theory or electrical theory, a conductor is just something that electrons can move through, and it's really easy for them to move. And the most common conductor in aviation is a wire. It's made out of copper. Some bigger airplanes have some aluminum wires, but copper, for its weight, is a really, really good conductor of electricity. Does anybody know something that conducts electricity even easier than copper? I can think of two things off the top of my head. They're metals, but gold. Yeah, gold is actually one of, if not the best conductor of electricity. But if copper wire, gold wire next to each other, all allow electrons to go through it the same amount. The gold is the heaviest, the steel is the second heaviest, and the copper is the lightest. Aluminum is lighter. But the problem with aluminum wire is if you bend it back and forth too many times, it'll fatigue and crack sooner than the copper wire is. And just so you know, gold, even if gold was heavier, it's way more expensive than the copper. So that's why most wires in houses and in cars and in airplanes are made out of copper. Because for the amount of cost, but mostly it's for the amount of weight, it's the least weight to allow the greatest amount of electrons. So if you push electricity, if electrons go through a conductor, go through a wire, it's going to get hot. It's going to get hot. For instance, anybody ever heard of a blow dryer? It's this device, you plug it in the bathroom, you hold on, you try to stick your finger in it, and then jump into the bathtub. And then dump the blow dryer into the tub that you're standing in. Isn't that the correct way? Isn't there a tag on it that says only operate this while you're standing in water and then drop the blow dryer into the water? Oh, that's what you're supposed to do with the toaster. Okay. Well, the toaster works too. Have you ever looked in a blow dryer? Can you see anything that changes color inside of a blow dryer? There's a coil, and what color does it change to? To bright red, yeah. So what's happening is that coil is just a conductor, and electricity is going through it. A lot of electricity. So it gets hot. That's how blow dryers work. That's how toasters work. That's how ovens work, electric ovens. Because a special conductor has enough electricity going through it that it gets hot. Okay, now most of the wires in flying machines, and cars for that matter, we don't want them to get that hot. So we use nice, reasonably pure copper, and it doesn't resist the flow of electrons. If wire has resistance, that means it stops some of them. And when that one electron stops, it gives off energy in the form of heat. Anybody ever notice the old school light bulbs, regular old school incandescent light bulbs, they get hot? Well, when electrons go through the filament inside of it, those electrons give off energy in two forms. One is in the form of heat, and the other is in the form of light. That's what nice thing, and that's the problem with incandescent light bulbs, is more than half of their energy they use up turns into heat. That's why LEDs are much cheaper to run. They may cost more to buy, but LEDs use almost all their energy to create light instead of create heat. It's not that LEDs can't get hot, especially the strong ones. They can get hot. But they don't waste very much energy getting hot. They use their energy. That's why you can get an LED light bulb that uses 1/10 of the electricity, but it's twice as bright as a regular light bulb. It's because it's not using all that energy to create heat. All right, so if you don't have a lot of resistance, the wire won't get too hot. The second thing that electrons going through a wire or going through a conductor, in addition to heat, is that wire becomes a magnet. It becomes an electromagnet. There is a very, very close correlation. In fact, it's all tied together between electricity and magnetism. You can't have one. Well, you can't have electricity, electrons flowing unless you have magnetism. I guess you can have a permanent magnet. And if it's not moving, it won't create any electricity. You may have, even if you took a regular science class in high school and it wasn't the physics class, you took a nail and you took a battery, and around this nail you had a wire. You coiled it around. Question? Yes, they do. And no one dies. The great news is most airplanes are made out of aluminum, which is a very good conductor of electricity. The lightning actually hits the airplane, goes through the aluminum of the airplane, and comes out the other side of the aluminum of the airplane and keeps going. Now, at the point it comes in or the point it goes out, sometimes it gets a little hot right there and it may pit the aluminum, and you might hit it enough that when you, and because you noticed you got hit by lightning, somebody goes and looks at it and says, well, we need to cut this piece of aluminum out and put in a new piece of aluminum. But it doesn't go through the fuel tank. Because the electricity, electrons will take the path of least resistance. And aluminum, electrons can travel through aluminum way better than they can travel through the air inside of the fuel tank. So the lightning doesn't go through the fuel tank. It may go in the metal of the fuel tank. And on big giant jets, the wing skin is the fuel tank. They don't have a separate tank where they riveted it all together, fuel sealant. And now the structure of the airplane is the fuel tank. That way they don't have to carry the weight of a fuel tank around. So it works pretty well. No plane has ever been destroyed because of lightning, but at the moment I can't think of one. No, but I've been struck by lightning as a human being. It hurt a lot, and it burned where the lightning came in, and it burned. Lightning went in this ear, and it came out that ear, so I had a lot of burn marks on in my ear. And since there's very little in my brain, it went straight through my skull. I'm just kidding. I've never been struck by lightning. But usually it does hurt, and since electricity goes through you, it's going to get hot. You're going to get hot. And you think you're really hot, but you don't want that kind of hot. Right, and we're going to talk about voltage versus amperage. Maybe not today, but on Monday. So, if you did this experiment at some point, this wire around the nail has lines of flux around it. So the lines of flux go around it, magnetic lines of flux. And where the wire is concentrated, all the lines of flux concentrate, and they end up looking like this. The lines of flux end up looking like this. And one side becomes a north pole and the other side becomes a south pole. And now you can pick up, of course everyone knows, what can you pick up with this? Paper clips. Thank you very much. So you can pick up paper clips. Right. And if you put in 2 batteries, and you pump in twice as many electrons, so instead of a certain amount of electrons, you pump in twice as many electrons, you can now pick up, that's exactly right, you can double how many paper clips. So how much magnetism you get is based on several things, one of which is how many electrons are moving through the wire. One way you can do it is concentrate them and put them together into a coil. That concentrates them so the lines of flux are all acting together, so it seems like you have a stronger magnet. That's not really what's happening. You're just taking all these lines of flux that would have been spread out across 20 feet, and you're bringing them all together. It doesn't cost any more electricity. So what you're going to find is if you want an electromagnet, a magnet that's made because of, you're always going to see it wrapped up in a coil of wire. In fact, the wire is going to be really, really thin, and it's going to be insulated so the wire doesn't touch, but there's going to be like 100 or 200 or 300 or 400 windings or wraps of wire. So now you can use a little bit of electricity and have a very strong magnet. But yes, one way to do it is to increase how much electricity goes through it. Now, if it's just a straight wire, do I have a wire? If I just have a straight wire, the line of flux will be around it, but it's only going to be one. It's going to be spread out. It's going to be really weak. Now, if you took a compass and stuck next to it, you'd probably see the compass move a little. If you put the compass next to this, you'd see it move like crazy. So most of the time, if it's just one straight wire, you don't worry too much about the magnet, the lines of flux coming off of it, most of the time. All right. Don't worry, 6 minutes to go. There's two basic kinds of electricity. There's direct current and alternating current, DC and AC. I've read up on, has anybody ever heard of that hard metal group? DC, AC? Well, yeah, there's that group, but DC, AC, they're a cover band for AC/DC. No, I made that up. You guys will believe almost anything I say in class. The next thing you'll know, you'll believe it if I said I had an eye transplant. Okay, somebody chuckled. I appreciate that. So direct current is what you're going to find in your car. It's what you're going to find. You don't have to write this down, but it's what you're going to find in little airplanes. That's what's in your flashlight. Your phone has a battery in it that is a DC battery, but a bunch of the stuff inside of your phone runs off of AC. So there's stuff in your phone that runs off of AC, and there's stuff in your phone that runs off of DC. Same thing with or a TV. TVs, you plug them into the wall, that's alternating current, but some of them run off of DC. Has to convert DC into DC. It has a DC battery. So some of it will run off of DC, and some of it has to convert into AC. So you're going like DC, AC. You know, they play the same songs whether it's AC/DC or DC/AC. So I actually got a couple of you believe there was a cover band named DC/AC. That's not a bad idea, was it? That was not a bad idea. Just so you know, I thought of that just a minute and a half ago. Just a minute and a half ago. I didn't have that one ready. Okay, I'm getting 2 chuckles, so I'm going to take it. All right. So let's say we have a regular battery, and just for fun, we're going to use a flashlight. And this is 1.5 volts DC, and this is 1.5 volts DC. And somehow through the battery, and there's probably a switch, there's going to be a light bulb. So there's got to be a switch on here somewhere, and we have to have what's called a complete circuit. You got the electrons. Of course, everybody knows on batteries which side is positive and which side is negative. Surely everyone knows. Yeah, the side with the bump on it is the positive side. Huh? The right wire? Or the red wire, yes, the red wire. Except inside of a flashlight, I don't think they color code the wires. All right, so together, how many volts is this going to put out? Yeah, very good. It's going to put out 3 volts direct current. Direct current means as this battery is discharging, electrons are negative. You can think of a battery as having too many electrons on the negative side of the battery and not enough electrons on the positive side. So the negative electrons are always attracted to where there's not enough. So the negative electrons are always going to try to get back to the positive side. So literally, these electrons are going to try to leave the negative side of the battery. And if you close this switch, that's now closed, and you make a complete circuit and you let the electrons go, they'll keep going. They'll go through the light bulb. Of course, the light bulb would be bright. And the electrons will go back to the battery. And slowly these batteries will discharge. All of the time that the battery is discharging, The electrons are going in one direction. So a flashlight is a great example of a DC system. Electrons always go through it in one direction. Yeah. How does the what work? How does kinetic energy restore? You mean like regeneration? I don't know enough about Formula One racing to answer your question. You're saying that, but nobody in Formula One uses electric motors yet, right? They do to drive the car. Has that are electric cars, and there's no gas engine on it. Well, obviously, I'm not keeping up with Formula One racing. Okay, you're talking about in a car that has electric motors and batteries, you can have what's called regeneration or regenerative braking. What that means is, see how fast I can do it. You got to find a picture, find one with no pictures. There we go. So here you have the battery, and here you have a switch, and here you have a motor, and it's got a shaft out here, and the shaft spins around. All right. Okay. This motor, sometimes it can be a motor, and sometimes it can be a generator. So the system is set up, when you push down on the throttle, it gives electricity through the battery. This is the plus side, this is the negative side. And the electrons go in this direction, and the battery discharges. But just like a generator or an alternator on a car, so what this motor is doing is turning electricity into kinetic energy, right? Into motion. All right, we want something that will go in the opposite direction. That's a generator or an alternator on a car. It takes energy, rotating energy, kinetic energy off of the motor and generates electricity. But what we do here in regenerative cars, like I got a Prius, that motor, it's also a generator. So when I put on the brake, it stops giving electricity from the battery. It turns this into a generator, and it will now push the electrons. It'll suck the electrons off the negative side, and it'll push them back to the positive side and charge the battery a little bit. Now this is freaking you out because you said, Mr. Johnson, you said DC circuits, electricity only goes one way. We'll talk about this some more on Monday when you're less freaked out. So what are we going to do right at the beginning of class on Monday? We're not going to have a test. On Tuesday, Tuesday, because Monday is DMLKJ Day. Dr. Martin Luther King Jr. So what are we going to do on Tuesday? Quiz. Quiz. Open homework quiz. Open homework quiz. Tomorrow, we're going to be remote pilots. Hoorah!